Alright, I thought I'd get around to actually doing this video here. Sorry that it took me a while. I was actually just a little busy this last couple days. But anyway, this is problem number 78 from 4.9. And let's see, a model rocket is fired vertically upward from rest. Acceleration for the first 3 seconds is a of t, which is 60t. So I spent a little bit of time on this problem, kind of figured out a nicer way of doing it. So I'm going to go ahead and write down the details right here. They give me at least for, I'll write this way, for time between 0 and 3. It could include time 0 and 3, why not? We happen to know that a of t is equal to 60t. And that will imply that v of t, velocity, which is going to be the antiderivative of that 60t, will be 30t squared plus some constant. And I'm going to go ahead and treat this slightly differently than maybe how I did it in class. I'm going to go ahead and take care of these constants right now. So we do know, all right, but we happen to know the velocity of time 0 because we're just firing the rocket off at that moment is going to be 0. So this will imply that c is equal to 0. So now our velocity function, at least for the first 3 seconds, is just going to be a 30t squared. And now we'll go ahead and move on to maybe the position function for the first 3 seconds. Let me get a little more comfortable. I'm trying on my couch here. And I'll do position in blue here. So this will imply the position function will equal dividing by 3, taking the antiderivative would be t cubed over 3 times 30, or in other words 10t cubed. And then plus a different constant. I'm actually going to reuse my letter c. Well, I better not. I'll use d here. I'll just keep incrementing the letters. However, we know that the initial position is going to be 0. At least that's what I'm going to say. Okay. So that implies that d is equal to 0. So now we have the functions for the first 3 seconds will be, and I'll draw these in green here, for the first, for times 0 to 3, you have your acceleration function, you have your velocity function, 30t squared, and you have your position function. Let's see, that was 10t cubed. Okay. Now, as I was kind of going through and trying to figure out the best way to do this, one thing I kind of wanted to note is that it's going to be important for us to go ahead and note the accelerations, velocities, and positions at, or at least the velocities and positions, I should say, at time 3. So the velocity at time 3 is going to be 3 squared, which is 9 times 3, which is 270. That, by the way, is in feet per second. And the position at time 3 is going to be 270 feet, actually. All right, now I'm going to go back to the word problem here, see what else I have as far as information. Let's see, so first 3 seconds, at which time the fuel is exhausted and becomes a freely falling body. And I debated in class whether or not to make the assumption, but I'm actually going to go ahead with the assumption here because I couldn't figure out how to do it otherwise. So what I'm going to make the assumption is that we have, first of all, let me see how long this is going to, 14 seconds later. Okay, so that'll be the time 17. I'm going to make the assumption that the acceleration is going to be negative gravity, the acceleration due to gravity. And in terms of imperial units, that's negative 32 feet per second squared. Okay, so I'm just going to go ahead and go with that. And that will imply that the velocity, let me make sure that I don't have anything else here, 14 seconds later. Okay, so no, it doesn't say anything else. So we're going to go ahead and do the antiderivative here. So velocity at time t is going to be a negative 32t plus some constant I will call e. Okay. However, we happen to know the velocity at time 3 should match the velocity here, is going to be 270. So that should be negative 32 times 3 plus e. And let's see, that's 96. So if I add 96 to both sides, what is that? 370 minus 4, 366. E is equal to 366. I should probably double check my math there. 96. Yeah, it's 366. So this implies, and maybe I'll go ahead and write this in green over here. So from 3 to 17, this implies that, one, our acceleration is going to equal negative 32. And actually, I'm going to change that velocity function now I'm thinking about it. Actually, I'm totally going to change that velocity function now I'm thinking about it. Because I did this in class, I think it's a wise thing to do. Let's actually time shift this. I'll change the velocity function to look like this. Negative 32t minus 3 plus e. If you take the derivative of this, it'll still be a negative 32. The derivative of the constant's gone, and the derivative of negative 32 times t minus 3 is literally just negative 32. So this is an antiderivative. It's just time shifted, and what's nice about that is when I plug in 3 for t, that this whole entire statement, negative 32 times t minus 3, that will disappear. So this just means that e will be 270. So that's actually going to be kind of nice here. So I'll go ahead and fill that in. The velocity at time t is going to be a negative 32 t minus 3 plus 270. Okay. And now I'll continue on to get the position function. Let's see here. The position function is the antiderivative of the velocity. So let me go ahead and just take the antiderivative of the velocity. Remember, it's going to be this object here squared divided by 2. So it's going to be a negative 16 times t minus 3 squared plus 270t plus some constant f. Oh, and darn it, I'm going to time shift that t there. I keep forgetting about that. Plus some constant f. And again, we happen to know from our initial conditions here, or our conditions, that the position at time 3 should be 270 feet. So that means that when I plug in 3 here to the position function, it should pop out a 270. And if you plug in 3 into this position function, you'll see the first term disappears, the second term disappears, and we'll just return f. So this tells me now that our position function for all of time is going to be a negative 16 t minus 3 squared. I might run out of room here. Plus 270 times t minus 3, and then plus 270. I just can see where the edge of my recording screen is. And what I'm going to do now is just evaluate this at 17, mainly because I think I'm probably going to need those values. So I'll go ahead and in red find out what v of 17 is and what the position at 17 is. Those will likely become useful. And what I'll do is, let's see if I have my backpack around here. Just want to use a calculator. Sorry if I could pause the video, but I'm being kind of lame here. All right, let me go ahead, and velocity is just negative 32 times 14 plus 270. So I get a negative 178. Again, that's feet per second, so it's actually falling. That should make sense. And then the position, negative 16 times 14 squared plus 270 times 14 plus 270. It'll be 914 feet in the air at that time. Okay. All right. Now, let's see, go back to the reading here. After that point, let's see, 14 seconds later, the rocket's parachute opens and the downward velocity slows linearly to negative 18 feet per second in 5 seconds. So, I'm going to have to take care of that. So in blue here, I'll just take care of that. So at t equals 17, we know the velocity is equal to a negative 178. And at t equals 5 seconds 22, the velocity is equal to negative 18. It's decreasing linearly, so I happen to know that we have a linear function essentially, and see the slope of that linear function is going to be difference in output, so negative 178 minus a negative 18 over difference in inputs, 17 minus a 22. All right, which is going to be, let's see, plus 18, so it's a negative 160 over a negative 5. And let's see, 1632. Is that what it is? Yeah. All right, so I know it doesn't make sense to me for some reason. It's a negative. Yeah, that's right. That's right, because it's increasing. Okay. So, let's see. Let me just double check. That makes sense. Yes, it does. The velocity is very negative, and it increases to be not so negative over a 5-second period. All right, great. So now what I'm going to go ahead and do is write a velocity function based upon this. And the velocity function, let me get out my black pen here. By the way, I should write up here for, how have I been writing it? T between 17 and 22. Okay. The velocity function is going to be the slope, and I'm going to time shift this. Okay, plus the initial velocity, which is actually going to be a negative 178. Now, just double check my work here. When time is 17, t equals 17, the first term disappears and the velocity is negative 178, which matches this guy right here. Okay, so that works out. And then this is a linear function, so let's see what happens at time 22. Time 22 minus 17 is 5 times 32. I'm just going to double check my work here. 32 times 5. Okay, that's just my phone. You're going to hear my ringtone for a few minutes here. Minus 178. That's a negative 18. You get some good, great music in the background. That is the standard ringtone, sorry. Okay, so anyway, that's my velocity function there. And now all I need is my position function, which will be... Oh, by the way, if you're curious, let's see. Yeah, it looks as though the acceleration function is just a 32 there. I'll double check that, but it's the acceleration function is just a derivative, and that would be a 32. So that takes care of that. Position will be the antiderivative of the velocity, so we'll have 32, but it will be divided by 2, so it'll be a 16. T minus 17 squared minus 178 t minus 17. Shoot, I keep forgetting that. and then plus some constant, I'll call it g. All right. However, the position at time 17 should be 914. So let me write that in. But the position at time 17 should be 914. So if I plug in 17 for all these, you'll see that that should be g. So this gives me my next three functions. I'll write those, what have I been doing, green? So I'll write those in green. Even though I'm kind of rewriting the acceleration here, it's 32. The velocity is 32 t minus 17 minus 178. And finally, the position, which is 16 t minus 17 squared minus 178 t minus 17. Darn it, I didn't give myself enough room. Plus 914. Okay. All right. So far, so good. But we still have, let me read. The rocket then floats, quote unquote, to the ground at that rate. So from that point forward, we know that the velocity is going to remain at the speed at time 22, which is going to be a negative 18 feet per second. Let me go ahead and write in red a few things that I may need. First of all, I want to say that velocity at time 22 is a negative 18. That's feet per second, but they told us that. That's not that big of a deal. And the position at time 22 is equal to, and then again, I'll just grab a calculator here. 16 times 25 minus 178 times 25. No, 5. Uh-oh. I have to check my math on something really quickly. I think I may have made a mistake somewhere. 424. I'm going to just check really quickly to make sure I didn't make a mistake back here. Very, very quickly. Negative 16 times 14 squared plus 270 times 14 plus 270. 914. Okay, good. I was just making sure I didn't make a mistake. I didn't. Okay, so c5 squared and 5 plus 914. Okay, that's all correct. Good. Just double checking my work. That's all. Always good to do. All right, and then it says it just floats from that point forward down to the ground. So let's go ahead and for t greater than 22, we will have that the velocity is always negative 18. Oops, that's supposed to be a negative. And therefore, the position function is going to be negative 18 t minus 22 plus h. And again, the position at time 22 is 424, which therefore, if you plug in 22, that should be h. So now you have following. The acceleration, this is for, again, 22 and above. It's actually supposed to be an open interval 22. Sorry about that. For 22 and above, the acceleration is 0. The velocity is negative 18. And the position function is negative 18 t minus 22 plus 424. A little bit of a mess. Now, it does ask for a lot more than this, actually. Sketch the graphs, which you should be able to do. At what times as it reaches maximum height, you just find out where the critical points are. That's where the velocities are 0, or where they're undefined, which does actually happen. And then, does it? Yeah. Where the derivatives are undefined. So that's going to be, let's see. Nope, it'll just be where the derivatives are 0. So it'll be where the derivatives are 0. And so you go ahead and... no, it's where the derivatives are undefined. Sorry, I'm waffling on that, but if you graph it out, you'll be able to see where the derivatives are undefined. It's actually at the points where these functions meet. So you just go ahead and if the maximums or minimums are in there, you can check in there. And then when does the rocket land, you can do that using the position function, actually setting this last position function equal to 0. So I think it's pretty good, though. You should be able to do the rest of this just by the graph almost. All right, we're done.